favor this afternoon, given by the delegate, one of the delegates from the USA, his name is Professor Burt Davis from the Center of Applied Energy Research at the University of Kentucky. Dr. Bertrand's talk is going to be on the C14 tracer studies and reaction networks involved in the methanol to gasoline reaction.
I need the slides. Involved. I wasn't sure that I need to bring this to a Catalyst meeting, but for one person who may not, this is the ZSM-5 catalyst with the channel. It's an intermediate-sized pore opening, and this in here is where the methanol to gasoline synthesis takes place. Next. During the synthesis, if you change time, methanol conversion decreases. You initially increase in dimethyl ether as dehydration goes on. During this period, very little in the way of hydrocarbons are formed. You essentially establish equilibrium, and then hydrocarbons start being formed. Next slide. This presents this slightly differently. In this region, equilibrium of the oxygenates is primary reaction. There is an autocatalytic increase in conversion in this region, and then hydrocarbons are formed while oxygenates are present. In the latter stages, it is just hydrocarbon reaction presence of water. Next. One of the intermediates that's proposed is the oxonium ion, in which the oxonium ion methyl adds, it inserts so that you form C2. This leads to ethylene. If you increase this, you get higher carbon number hydrocarbons. Next slide. A second mechanism that is widely believed in is the carbene, where you form CH2 by dehydration of methanol. This carbene then inserts into carbon-hydrogen bond, leading to higher carbon number compounds. A third mechanism is the next slide. One in which carbenium ion is involved. You have first formation of CH3. The CH3 adds to ethylene to form C3, adds to form C4, and so on. And so in this, positive ion intermediate is proposed. Next slide. One way to test for carbene is to see what it does when it adds to propane. It should add statistically, so you should get 3 normal butane to 1 isobutane. Early work from Mobile indicated that this did happen. We used carbon-14 tracer study in which the methanol was labeled and obtained data that was not consistent with this. The next slide. This is the iso C4 to normal C4 ratio. With carbon-14, we can tell what is being formed from methanol. This gives a ratio typical of what you get in methanol to gasoline. But what is being formed from the propane is much higher iso to C4 than what is being formed from methanol, and is not consistent with carbene. Next slide. Studies were made in which carbon-13 has been incorporated here because of necessity of analyzing by mass spec. They have concentrated on the ethylene composition. If you start with carbon-13 labeled methanol, unlabeled olefin, you have the possibility, if the initial step is C2 formation, to form dicarbon-13 ethylene. The other 2 possibilities are here. It was concluded that they had shown what the mechanism was, but as I show on the next slide, this is the equilibrium distribution of ethylene. Don't know if it'll... this is what was obtained with small crystal ZSM-5, and with this ratio, the high silica ratio, and the distribution is very close to equilibrium, and as I show in the next slide, This is the composition measured experimentally. The open circle, this is the composition at statistical distribution. And so starting where you would form from methanol, carbon-13 labeled ethylene here, they are this close to being at equilibrium. Next slide illustrates a similar case in which this is the experimental, this is what you would get a statistical distribution. Third one, just to convince you that they are close, this is the furthest they were from equilibrium. So these carbon-13 tracer studies are somewhat like being very close to chemical equilibrium. It's very difficult to extract mechanistic data from data that is at equilibrium. It tells you that you are close to equilibrium, but it doesn't tell you what pathway you follow in getting there. Furthermore, all of the compositions were different, and so you can't establish a common pathway. Next slide. This emphasizes an estimation of how close they are to equilibrium. These are Australian workers and mobile workers, and in all of these tracer studies, we believe that they are so close to a statistical distribution that even though they're consistent with the mechanism, they don't prove the mechanism. Next slide. Hightower did carbon-14 tracer studies with a nickel-containing ZSM-5. What is shown here is the radioactivity per carbon, and if you have statistical distribution, all of these should have the same activity, and you see that the experimental data would say that Hightower's data was also obtained where isotope equivalency has been obtained. It's essentially the equilibrium case, and so you cannot extract mechanistic data. Next slide. This is data of Kading. This is typical of what you would expect for a Anderson-Schultz fluoride plot for Fischer-Tropsch synthesis. It's consistent with C1 adding to C1 adding to C1, a polymerization of C1 species. Next slide. This shows why you should pay attention to thermodynamic data. This is what you would get at chemical equilibrium, and so it's going to be very difficult to tell whether this is from equilibrium or whether this is from polymerization. Next slide. This is data that we obtained, which again gives the Anderson-Schultz fluoride until you get to aromatics, where it now deviates because of alkylation of the aromatics. It is tempting to say it is consistent with C1 polymerization, but it's so close to the thermodynamic control that I don't think we should reach a conclusion that it is C1 polymerization on this data. Next slide. Now, these are mixtures that we have run with ZSM-5 where the silica to alumina ratio is about 30. And this is the sample that Mobile was giving out. With all of these mixtures, we obtained data which I can illustrate in the next slide. The activity increases with carbon number. It all fits on a straight line, and this is the line you would expect for carbon equilibration, if you will. That within ZSM-5, with the high alumina content, high acid content, we do not get anything outside of the channel that has not isotopically equilibrated. Again, this data is of little value in deciding what the reaction mechanism is. One point that I want to make is that ethylene is different from the other carbon number compounds in that it has not attained equilibrium. Next slide. This shows it doesn't matter whether you start with methanol labeled or propanol labeled, you still get the straight line. Because of different carbon numbers, and we're making these on the basis of 1 for methanol and propanol, you get two different lines. But as shown on the next slide, if you make the activity of C3 equivalent, then you get equivalent data from the two labeling experiments, and it's equivalent to the isotopic equilibration. Next slide. Since we were frustrated in using the mobile zeolite with the silica Al2 ratio of 60, we got one which has a much higher silica to alumina ratio so that the acid site density is lower. And in the next slide, this is the catalyst pretreatment. We diluted the catalyst in alpha alumina, which is inert. These were run at 300 degrees, 1 atmosphere. We do the chemical analysis by GC, and we determine the carbon-14 activity with a proportional counter that is in series with the gas chromatograph. Next slide. This is data where we are labeling methanol or ethylene, running it in this ratio over the silica light at 300 degrees. If we look first at the data in which ethylene contains the carbon-14, we see that C2 has a relative activity of 1. The products that we are making from C2 are constant activity. This now is the first time we've been able to obtain an isotope distribution which is different than chemical isotope equilibrium. And so now we think this applies to mechanistic data. This is consistent with C1 adding to C2, the inert methanol contributing the third carbon, the fourth carbon, the fifth carbon. And so this is consistent with the olefin being alkylated by the methanol. If we reverse the label, so we now put it in methanol and use unlabeled ethylene, we see that ethylene is very low activity. And so that the methanol is contributing essentially nothing to the C2 fraction in this case, only 1 in 1,000 or so. Ethylene are formed over what we have present. The addition is such that now 1 carbon-14 containing methanol is added to C2, relative activity the same as methanol. Here we have added 2, the activity is now 2 and 3. And so both labels are consistent with ethylene forming higher carbon numbers by C1 addition, and doing so in a series of a growing chain. Notice also that C2, if it formed a dimer, would have a relative activity of 2, and the point would be up here. So that essentially none of the ethylene has dimerized. This is different than the data I'm going to show you in a minute, where we are starting with propene instead of ethylene. And so for this, just remember that the data with ethylene is consistent with C1 addition to a growing chain, and that there is essentially no dimerization, and there is data which now can be used for mechanistic interpretation. Next slide. This is to show you a gas chromatogram, and then the carbon-14 trace to show you that we are getting essentially baseline separation, and that we are able to measure the activity of individual compounds. And in the next slide are some of the compounds. All I want to show you is that the labeled activity is very close to 1 for each compound, so that there is not a selective isotope incorporation into the individual compounds, that all of the compounds are within a carbon number, have essentially the same relative activity. Next slide. Now with that, we're going to do a series of experiments in which we take only propene with nitrogen. Now we have essentially a chemical equilibration of compounds, so that C3 is dimerizing, trimerizing, and then cracking to give you a chemical equilibration of compounds. If we take 1 hexene and do the same experiment, we get essentially the same distribution. Again, this is because of olefin cracking. If we put methanol in with the propene, we see now we get a quite different picture. All of these are run under the same flow rate, same temperature, all conditions are the same. Now C3 undergoes much less of this scrambling. we are forming predominantly C4, so that now under these flow conditions we are getting alkylation. And it is consistent with C1 adding. Next slide. This is showing carbon-14 isotope distribution. The square are just to show you that if we label the propene with carbon-14, that every carbon number grouping that we have, including C2, has the same relative activity. Each one of these increases by 1. The slope of this is 1, which is what it should be, because everything on this line is being formed from carbon-14 propane. When we now label the propane, unlabeled methanol, we see that the C3, C5, C7 form a data activity which is a reasonably good straight line, but now they fall below the line that we would expect if there was complete equilibration. The reason for this is that we have the unlabeled methanol. It is adding to this. The activity of the C2 is much, much lower than what would be the case if it were equilibrating. And so this data says that for the compound C4 is being formed essentially by alkylating the labeled propene. The activity of C4 is essentially the same as C3. It is decreased slightly because within this equilibrating pool we're adding unlabeled carbon-14. And we have made the C3 be equal activity. The C6 is, C6 should be slightly higher activity than the C5 that you would expect if it's formed from C5. This indicates that propylene is different from ethylene in that it is forming a dimer. This is much better shown when we reverse the label, and the next slide shows the label being reversed. I should have drawn lines in this, but it's too late now, so I'll have to do it with the laser pointer. This is the data that you just saw where we had the propene labeled. This is the activity of the propene. The C4 is only slightly higher, which would be consistent with almost all of the C4 being formed by C1 alkylating carbon-14 containing propene. But now when we look where we have labeled methanol and unlabeled propene, the activity of propene is still essentially 0. The activity of C2 is much, much lower in this case, much higher when we start out with labeled methanol, but much lower when we start out with unlabeled. It is forming only slight amount of C2 with respect to the amount of methanol reacting. In this case, the activity should stay constant. It is essentially being constant, except for the C3. C6 again is much lower activity, and you see this is consistent again with C3 forming a dimer rather than being formed by alkylation of the C3 being alkylated by labeled methanol. This increases almost by a relative activity of 1. This is what you would expect if methanol adds to C3. What is happening in this case is that this is low activity because of the cracking reaction is occurring simultaneously with the C1 adding to the olefin. Next slide. I will try to summarize this in words. When we have labeled methanol, propene unlabeled, the activity of the C3 is only about 1/1000th of the propene, so that essentially no C3 is being formed directly from methanol. The activity of C4 is such that at least 75% of the C4 is being formed by adding C1 to C3. So that alkylation of olefin is the major pathway, and as I say, less than 1 in 1,000 C3 is formed from methanol. The activity of the C5 is about 1.42 times greater than C4, and again, approximately 70% of the C5 is formed by C1 addition of C4. Next slide. This is the given condition with the carbon-14 labeled propene. The C3 to C6 chemical equilibration, near chemical equilibration, the carbon-14 and the C2 to C7 falls on a straight line. This is what you would expect if you just have propene. If we look at the same condition with methanol, carbon-14 methanol present, we see that methanol is dehydrated. The catalyst has activity for converting methanol by dehydration. It forms dimethyl ether, but very little hydrocarbon. The methanol at 300 degrees, at this low vapor pressure, at this high flow rate, is only forming the methanol dimethyl ether equilibrium. There are no olefins present. When we put an olefin present, in this case propene, we now form a large amount of hydrocarbons. The C4, C5, C7 have essentially the same activity as methanol, saying they are formed predominantly by C1 alkylation. C6 is formed primarily by dimerization of unlabeled propene. And so the propene is much less active than methanol. All of this is consistent with C1 alkylation of the propene. If we have labeled propene, unlabeled methanol, it's hard to see, but I'll just summarize it. Don't worry. I can say it's consistent with this data. You can't read it, and so you should have to believe it then. But if he did lift it up, it is consistent. Next slide, I summarize what I would say I view, or we view, the mechanism to be. There is an equilibration of chemical species within C3 and higher within the channel. This equilibrating soup has C1 added to each one of these carbon numbers. The C2 species is outside of this equilibration, and so it seems to me that C2, when you have olefins present, the formation of C2 is a trivial part of methanol to gasoline synthesis. Once you get C3 olefin, this equilibration and C1 adds within this carbon number equilibration of olefins. Superimposed on this is dimerization, trimerization, cracking, which helps to redistribute the carbon number in here very quickly. Thank you.
Questions on this thing? No questions?
That's the easiest mechanism sale I've ever made.
One question, but what do you think is the influence of changing the silica alumina ratio of the zeolite? Besides allowing you to do the mechanistic studies.
Well, I for a long time understood that the pore channel was necessary for methanol to gasoline. And so if synthesis, if that were the case, then I would say that changing the silica to alumina ratio decreases the acidity, it decreases the secondary reactions, and so therefore we are not getting isotopic equilibration because the number of acid sites are much lower than in the higher one. Recently, ARCO workers published a paper in which they contend that they have poisoned the acid sites which are on the interior, and they report for exterior acidity, methanol to gasoline synthesis occurs. It has the same distribution as in products as that in the interior, and so we are now making the these two forms of acid ZSM-5s and seeing whether, in fact, with the tracers, we do get the same results on acid sites on the exterior by selectively ion exchanging so that you can only form acidity on the exterior, or essentially dominate with exterior acidity. So that's a long answer to say, if it isn't acidity, I don't really know.
Alex?
Is the mic here? Well, this response to the question prompts a question to me, from me, and that is, if it's only the exterior acidity that matters or plays a role, why can't you use amorphous silica alumina? Is it just a question that that would coke too fast to make a practical catalyst?
Well, the reason that we're doing the studies is that we didn't exactly buy the story that the exterior acidity was adequate for methanol to gasoline synthesis. But ARCO has done a lot of work on this and was trying to sell a process based on it. And so I assume that the only question would be whether they were able to exchange so that they only had acidity on the exterior and didn't have any in the interior. And so in both cases they had interior acidity. But we are in the process of running these conversions to see whether that's really the case. Because it upsets, what, 30 years of folklore of why ZSM-5 is the greatest catalyst in the world, and you hate to see 30 good years of sound knowledge go down the tubes in one experiment, so we'll provide a second one.
Are there any more questions? One thing you might be interested in, but probably know that now there are a whole series of ZSM-5 type materials available commercially for PQ. So you can vary the silicon-aluminum ratio, I think about 8 different ratios that might help you.
I wasn't aware.
You won't need to synthesize them yourself. Now let us thank the speaker for no more questions.
Next speaker is Professor Young Yu